So the name of the game today is thinking about rational expressions. And when I say the word rational expressions, what I'm really talking about are just fractions. But in those fractions, we have variable expressions on the top and the bottom. The good news is that we know how to do arithmetic with rational expressions because we know how to do arithmetic with fractions. So just as a quick reminder, before we get started with the tough stuff, let's go back to our first run through the course material and think about the more straightforward stuff. So this problem is going to ask us to multiply these two rational expressions together. But if you don't remember how to multiply fractions, we're not going to remember how to do this. So let's just do, as a quick simplifying example, how to multiply just two numerical fractions, one by another. So let's say I want to multiply 5/6 by, I don't know, 7/10. No, not 7/10. Let's do 3/10. So how would I carry out this multiplication? How do you multiply two fractions? Straight across, exactly, right. So multiplying is the most straightforward thing that you can do with a pair of fractions, right? Straightforward both literally and figuratively. Right? We're going to multiply straight across in the numerator and the denominator. That's going to give me 15 upstairs. It's going to give me 60 downstairs. And so I'm going to have 15 over 60 as the result of this multiplication. But then what should I do before I'm finished with this problem? What else might I want to do with this fraction? Simplify it. So this is where things get interesting for us today. Because how do we simplify a fraction like 15 over 60? What do we have to look for? What are your thought processes? What's radar screen? Right, exactly. In order to simplify a fraction, what we need is we need a factor which is common to the numerator and the denominator. Something which is both a factor of 15 and a factor of 60. So what can you think of that's both a factor of 15 and 60? 15 happens to be both a factor of 15 and 60. 15 is 15 times 1, and 60 is 15 times 4. Right. So because of that, I'm going to add one little extra step into our simplifying process today. I'm going to actually write out each of those factorizations. 15 times 1 and 15 times 4. This is a step we don't always write out, but I want to write it out today for a specific reason. But since we know that 15 is a common factor, what does that allow us to do? When I simplify, what do I actually end up with? 1 over 4. Because the common factor of 15 can be divided by in the numerator and denominator. It's what we sometimes call canceling, right? And so what will often happen at this point in a course like ours is that people develop a comfort level with simplifying numerical fractions, but then they don't apply the same thinking and the same logic to simplifying fractions that have more going on. When in fact the same logic all applies, right? That if I want to multiply these two fractions, one by another, what do you think should be the first thing I do? Based on what we know about how to multiply numbers across. Oh, I just gave it away. Let's do it. Right? Anytime we multiply two fractions, we do the same thing. We multiply across the numerators and we multiply across the denominators. That doesn't change. Even though my fractions have variable expressions in them, that's going to be my step. Right? Multiply across this way and multiply across this way. Of course, when I do those multiplications, the results are going to still have variables. I mean, they're still going to be variable expressions. So we're not going to be able to get around that. But at least we're kind of living in the right space here. But, and now here's the first place where it's easy to screw something up. Each of my pieces of each of my fractions are made up of multiple terms, right? I have x plus 2 over here, so that has two different additive pieces. And if I'm going to multiply that by 4x plus 12, I need to make sure that I'm multiplying the whole thing by the whole thing. So the first thing that you might try reminding yourself to do in problems like these is to start just by adding parentheses around each original numerator, each original denominator. just to make sure that once we actually go forward and do the multiplications, that we're actually multiplying everything by what it needs to be multiplied by. So at the end of that, what I would end up with is one set of parentheses times another set of parentheses, and then downstairs I'm going to have another set of parentheses times another set of parentheses. I'll fill in everything else here. X plus 2, 4x plus 12, x squared plus x minus 6, and then x minus 3. And then I would just put my fraction bar in. And right here is an answer to this question, right? What do I get when I multiply these two fractions? I get that. Except what haven't we done? Yeah, that's the problem. The problem in working with rational expressions is often not in doing the actual arithmetic itself. It's in doing the simplifying where people screw things up. So here are some of the things that often happen. I'm going to play the role of Math 095 student. And I look at a problem like these, and I know this because even some of you did this on the first exam, which I can forgive because we hadn't had this conversation yet. But sometimes students will look at this and say, what do I see? Well, I see a 12 up here and a 6 down here, and I know that those two have something in common. Right? So why don't we just reduce the 12 and the 6 into a 2 on the top and a 1 on the bottom? Anyone see what's wrong with that logic? Here's what you can take home, tattoo it on the inside of your eyelids, whatever you need to do to engrave it upon your collective memories. We cannot factor. I screwed up the saying already. We cannot cancel that which is not a factor. And when I say that, what I mean is we can't cancel something unless it is a factor of the whole numerator as well as the whole denominator. So 2, or 6, I guess rather, 6 is a factor of 12, and it's a factor of 6. But it's not a factor of this whole numerator and this whole denominator. We can't selectively go into one of these additive terms and just sort of reduce it, right? As long as there's addition or subtraction happening upstairs and downstairs, you got to factor first. We have to know what the factors are before we can hope to cancel them. So if we're thinking sort of procedurally about this, really the message here is before canceling, before you can do any canceling to simplify, completely factor everything in the numerator and denominator. And so this is why factoring is so important to our investigation of rational expressions, is that if we don't know how to factor, then we don't know what we can cancel. And if we don't know what we can cancel, then this fraction is never going to get any simpler than how it's written. So our job is to somehow do something along the lines of what we did over on the lower right, where we had 15 and we had 60, and we said, oh, we can break out 15 into 15 times 1 and 60 into 15 times 4. And now that we've written them out in this way, we can see that 15 is a common factor, and therefore we can cross it out. Right? It's a multiplicative piece of the numerator and the denominator, which is good. The 12 and the 6 were additive pieces. That's not good for canceling, right? Because addition and division don't work that way. They don't have that kind of relationship. Right? So there's our task. We now need to factor the numerator and the denominator as much as we can. So let's start with something that we already know how to factor from our first run through the course material. How about 4x plus 12? How can I understand what the factor of, how the expression 4x plus 12 factors? What do you think? How did we learn to do this a few weeks ago? So you look at these two terms, 4x and 12, and note that both of them have a factor of 2 in common. So we can factor the 2 out of 4x and get 2x, and factor a 2 out of the 12 and get plus 6. So we could factor the 4x plus 12 as twice the quantity 2x plus 6. Is there another way to do that? Yeah, we can actually do a little more than 2. We can actually bring out a 4. 4 factored out of 4x leaves me with how much? x, and 4 taken out of plus 12 leaves me with a plus 3. There we go, cool. And that's the best we're going to do, because x and 3 now have nothing more in common that we can bring out. So then the first thing that I'll do, I'm going to kind of keep tabs down here, is I can take the 4x plus 12 and replace it with its factorization, which we now have said is 4 times the quantity x plus 3. In the numerator, we also have this x plus 2. Can't really do anything with that, so I'm just going to keep it out in the front. So now all 3 of the terms that live in my numerator, sorry, both of the factors that live in my numerator have now been completely factored in turn. So that's everything as far as the numerator goes. In the denominator, I have this x minus 3 that we also are not going to be able to do anything with. But there's still one more factor that we might be able to break down further. A number like we had 60 over here, that if we can break it apart, then maybe we can find one of its factors that matches up with one of the factors upstairs that allows us to cancel. So now the question is, how do I factor x squared plus x minus 6? So our next step now is to contend with the question, how do I factor x squared plus x minus 6? The reason this is a tricky problem, right, how to factor x squared plus x minus 6, is that it doesn't yield to the methods of factoring that we already know in the course. Because so far, we only know how to factor when we can look at all the terms and find something that they all have in common. Well, what do all 3 of these terms have in common? First of all, how many x's do all 3 of these terms have in common? Well, the first term and the second term definitely have 1 power of x in common, but what about the third? It's got none. And so if the third's got none, that means that the 3 of these terms can have none in common, right? Unless all of them have an x, we can't say that the greatest common factor has an x. So let's say 0 powers of x in common. What about the coefficients? The coefficients are 1, 1, and 6. What do those 3 numbers have in common? Just 1. Well, that's dull. That means that not only are there no powers of x that all 3 of these can agree upon, but there's also no interesting positive integer factors that they can all agree upon either. Right? And so the best that we can do if we're trying to factor out a greatest common factor of all 3 of these terms is to factor out the number 1. But when we factor out the number 1, nothing happens. So that's bunk, right? We can't use the technique that we already know to factor this because our 3 terms don't have anything that they all agree upon. They don't have anything that they all share. So that means we need a new jam. We need something that we haven't seen before. Does anybody remember how to address factoring one of these things? We call it a quadratic trinomial. So I'm going to unpack that sentence just for a minute while you're thinking. It's a quadratic trinomial. Why is it quadratic? What does that number, or what does that word tell us? Yeah, the word, it's funny, the word quad actually tends to be the root in Latin for the number 4. But in this case, that 4 represents the 4 sides of a square, and the square represents the exponent of 2 here in my expression. So when we say the word quadratic, what we really mean is an expression which is a polynomial of degree 2. So the highest exponent that we see here is 2. Now unpack the word trinomial. What do you think that means? Where's the tri coming from here?
There are 3 digits.
Yeah, exactly. We have 3 pieces which are being added or subtracted together, 3 terms in my thing. So that 3 explains why this is a trinomial. So those are the kinds of expressions that we now have to figure out how to factor. For today, in our intermediate level run through the course, we are going to consider only quadratic trinomials that have a leading coefficient equal to 1. So for today, all of our examples will have nothing in front of the x squared except for a 1. Right? If we change that, if we have something that's not 1 in front of the x squared, we actually need to use a slightly more sophisticated technique. So that's something we'll do in our advanced run through the course. In a couple weeks, we'll see that. Okay, so this is a quadratic trinomial. And here's why our current methods are insufficient in some ways. what I'd like to do, let's talk about what we do know how to factor in this expression. We do know how to factor x squared in a meaningful way. How can I break apart x squared into a product of two interesting things? What is x squared? Blank times blank. X times x. That is probably the most underrated factoring fact in the universe. X squared is x times x. And that's important, because that means that the x squared part of this, we know what to do with. Every single time we factor, we're going to be able to write this as a product of two things, and in each of those two things, one of the terms is just going to be straight up x. So we know that much, at least. We know that we're going to be able to break this apart into two pieces, and each of those pieces is going to have one term that is just x. Let's move this down here. So we know how the x squared is going to break apart. Okay, how about minus 6? So this is where things start to get interesting. If we can kind of comfortably think about how to break apart a number into two pieces, that can help us to make some more progress. So now is a time when we can think about what are the different ways to break apart the number 6, or rather the number negative 6, into a product of two things. What's one example? How do I multiply two different numbers together and get negative 6? Negative 2 and positive 3. Sure. So there's one possibility. Let's list a few more. What's another possibility that multiplies to negative 6? Negative 3 and 2. Sure. And let's put on one more, just so that we have the full spectrum of possibilities. Negative 1 and positive 6. Sure. So now, unlike x squared, there's a whole variety of different ways that we can break apart negative 6 into a pair of factors. So now the question is, which one of these possibilities is going to give us the factorization that we want? Let's take, just for starters, let's take negative 1 times 6. So imagine a world in which I split apart this negative 6. And when I say split apart, what we're really doing here is we're kind of going to the outside of my little factoring grid here and writing those factors down, negative 1 and positive 6. And at this point, now the x squared works. It's x times x. The negative 6 works, negative 1 times positive 6. And we've accounted for the first term and the last term in our trinomial. So the real question is, have we accounted correctly for the middle term? If I multiply out this factorization, am I going to get the plus x in the middle that I need? And the nice thing about my multiplication grid is I've already got it set up to figure out what the answer to that question is. So I'm going to try it. I'm just going to multiply 6 times x. It's going to give me 6x. And I'm going to multiply negative 1 times x. Negative 1 times x is going to give me minus x. So here's the algebra that we're really kind of representing in this grid. We're representing the idea that if I multiply x minus 1 times x plus 6, what I'm going to get is x squared minus 1x plus 6x minus 6. But that's not completely simplified. What can I simplify up here? Yeah, the 6x and the x happen to be like terms. So how do I combine these two like terms together into a single? Add together their coefficients. And the coefficients are negative 1 and 6. And when I add negative 1 plus 6, I get negative 5. Positive 5. Yeah, you said it right, and then I said it wrong. X squared plus 5x minus 6. So from this work, what do I conclude? It doesn't work. Right? We accounted for the x squared, we accounted for the minus 6, but our middle term is screwed up. Right? So that's no good, but that just means that we just need to try a different combination over here. Right? A different way to break apart negative 6 is going to be what's required to get the factorization that we need. So which combination is going to work? What do you think? Negative 2 and positive 3. Now, how do you know that that's going to be the combination that works? Because I agree with you, but why? Right. Right.
-1.
Exactly.
It's going to give you that negative x, or the positive x.
Right. So the reason that you knew that -2 and +3 was the right combination is that those two numbers added together give me how much? What's +3 plus 2? Sorry, +3 plus -2? 1. And 1 is exactly this middle coefficient that we need on the x. So that works, and the great thing about factoring is you can always check your work, right? Multiply this back out, x squared minus 2x plus 3x minus 6. And sure enough, when these two middle-like terms are combined, we get x squared plus 1x minus 6, and that's what we hope to get. So when we look at this from a bird's eye view, what did we really do in order to determine this factorization? The first thing we did was we found a pair of numbers that multiplied together to give me -6. But we don't want just any pair. We want that pair that also adds to +1. Right? So you end up playing this little reverse guessing game in your head, where the first thing you think of is how to break apart that constant term, how to break it apart into pairs that multiply together to give me that one. Because that's a pretty small list, usually. And then from that list of possibilities, find a possibility that has the property that it also adds together to give us the middle term that we need. And that's going to be the pair that wins. I call it the sum and the product game. The product needs to be -6. The sum needs to be +1. There's only one pair of numbers that satisfy both of these criterion at the same time. That's the winner, +3, -2, and there's our factorization.
Are you putting this on Blackboard?
Now that we know how to factor this thing, let's remember why we were factoring it in the first place. We were trying to simplify this product of two rational expressions. And now we know that x squared plus x minus 6, I'm going to recreate the little factoring grid that we had on the other screen, that x squared plus x minus 6 can be factored as x minus 2 times x plus 3. So get that written in here. X minus 2 times x plus 3 does give me x squared plus 3x minus 2x minus 6. And that's the factorization that we want. X plus 3, x minus 2. And now we have finally achieved our goal of factoring everything in sight, which is my first recommendation in any rational expressions problem that you're ever working with. Your first instinct should not be to multiply things out. Don't use FOIL on this and then use FOIL on that, because that's going to make your life much more miserable. Because when it comes to simplifying, factoring is what we want. So resist the urge to multiply things out, and instead go the other direction and factor. Because now that everything has been factored, now we're in the situation like we were in over here, where once we see what all the factors are, now the common factors jump right out at us. What common factor does the numerator have with the denominator here? X plus 2. Wait. Not x plus 2. But x isn't a factor of the numerator or denominator, right? Yeah. If we had like an x sitting out here as another factor, then I would agree with you. But x is the role that x is playing here is it's a term within this factor and a term within that factor. It's not itself a factor of the whole thing. Spencer said it. Brittany?
Yeah.
X plus 3. Yeah. So the factors, we group the factors off by parentheses. And so we can directly see right here that x plus 3 is the one and only factor that the numerator and denominator in this expression share in common. Every other factor is not shared by the numerator and denominator. So this 4 doesn't live down here, so we can't cancel that. The x plus 2, almost but not quite, right? But almost doesn't count in this context. We can't cancel that. X minus 2 isn't upstairs. X minus 3 isn't upstairs. So the only things that we can cancel are the x plus 3's from the numerator and denominator. And then everything else is stuck. It becomes part of our final answer. 4 times x plus 2 over x minus 2, x minus 3. And if you want to stop there, you can. I'm fine with it. I think the online system is fine with it. Cross my fingers. If you prefer to multiply things back out, you may. And so I'm just going to include that in here for posterity, just as an optional last step. We can multiply 4 times x plus 2 to get me 4x plus 8. And then in the denominator, we can FOIL. X minus 2, x minus 3 turns into x squared minus 5x plus 6. That last step is optional. If you don't like leaving your answer in factored form, you can do that. But honestly, even from a mathematician's standpoint, it's better to just leave things factored, if at all possible. Because if there's any additional algebra that you ever have to do with something like this, it's much easier to do when it's factored than when it's multiplied out. So if nothing else, working a lot with rational expressions will get you a lot of really good practice in how to factor. And without a strong foundation of how to factor, working with rational expressions becomes much harder, if not impossible, in some cases.